extra. Let me share my screen. Right. So the last time actually we were talking about conservation laws. And remember that one conservation law that I talked with you is about the conservation of energy. So let me come back to the same topic. Now the first one is, if a system doesn't change explicitly with time, right? So there was actually a question that I guess Anomi asked about this as well last time, about maybe what I mean from this explicit, what may be the meaning of this explicitly dependent with time, right? So you will probably understand that today as well. If a system just give me a minute. Just hold for a second. So I'm just doing something else here just to fix my writing. And also for your tutorial, you have time until next Monday, right? Since you were not sure like whether we are going to go online or do lectures on time. So you have time, even if you have like, I guess, extra few days now to finish it. Now with the completion of about this thing called conservation laws, then you will be able to finish that tutorial. And the second tutorial should be available during next week for you to complete for the next sections that we talk, which will include, of course, all the sections that we did up to now. So, right, so it came back. Right, so what I talked last time is that if a system doesn't change explicitly with time, so basically this is similar to system is same at different times. I mean, one just simple example is think about your room at home, or think about just your home, right? If you go somewhere and come back after like few days, home will be right in the same situation, right? So it will not change basically, right? Space and everything will be similar. So this is something like that. So if there is nothing changes over the time in the system, then we used to tell that then if you write the Lagrangian for that particular system, it will not change with the time, right? It will be constant. The idea is that we normally write Lagrangian as a function of generalized coordinates, generalized momentums and the time. And this time dependence of the Lagrangian T that will be not there, right? If the system doesn't change explicitly with time. And you may have a question that this q dot here, inside that you have, it's a time derivative, right? But that's a different thing. And this is what I mean, that the Lagrangian does not depend explicitly on time. So that means this component right here, dabba L over dabba T, this one should be equal to 0. And this is what we talked last time, where we stopped the Lagrangian does not depend explicitly on time. So which means the partial derivative of the time should be equal to 0. Right? And then you can write the total differential of the Lagrangian, that is dl over dt. So that will be equal to, you know how to write a total derivative, right? You have been doing this for some time now. I will write it directly. So dl over dt is, so the Lagrangian basically depends on three functions, q, q dots and t's. So dabba L over dabba q I, and then you should have another term, right? Then the q with respect to t, that is dabba q I over dabba t, and that can be written as qi dot. So I hope you can understand it. And there is an interesting notation that I am going to use here. You can see that you have the indices here, I and I, right? Normally what you would do is you should have a summation symbol right here, just to uh, uh, have this idea that you have to sum over all the generalized coordinates, right? Qi is just one of those, and you have to sum over all the coordinates, right, in the Lagrangian. So that's what we do. But I am not going to have this summation here. So I'm going to take that out. And when you have same indices like Qi right here, and then multiplied by the same index right here, this actually indicates that you are summing over I terms, right? And we don't need to write the summation symbol here. And this is actually introduced by Einstein, and this is actually called the Einstein summation notation, right? If you just Google about this, you will find more information. And this is a way of writing these complex mathematical expressions in a very simple way, right? That's the idea. And right. So just keep in mind that when I write it in this way, that means the summation is there. So that's why what I want to tell. So that's one part. And then you have the next term, qi dot. So you have to take the derivative of that qi dot. And then qi dot, again, you have to take the derivative with respect to time. So that means qi double dot. And then plus, you have this term time. So it is directly depend on time. So it will be dabba L over dabba T. Now, when the system explicitly does not depend on time, then what happens is this term will be 0. Right? So that's what we have talked to now. So which means the only remaining thing is this term right here for the dl over dt. Now for this one, there is something that you can replace. That is daba L over daba Qi here, right? If I write the Lagrange equation, what we write is d over dt daba L over daba Qi dot minus daba L over daba Qi equal to 0, right? And you can see that this term right here, daba L over daba Qi should be equivalent to this term according to the Lagrange equation. And then you have this daba L over daba Qi term right here. So let me show it. So these two terms are similar, right? So you can replace it from this term right here. So let me do that and write this one. So dl over dt is equal to daba L over daba Qi. Sorry. So daba L over daba Qi is what we need to replace. So that will be d over dt daba L over daba Qi dot and then plus the other term would not change. It will be daba L over daba Qi dot and then Qi double dot. Now I can take
Sir,
yes.
there should be a QI dot in the first term, I think, sir.
Um, yes,
D
I
over
guess you are
dt
correct.
daba
Yes,
L
yes. Thank you, Sajini. So yes, there should be a Qi dot because this Qi dot comes. This Qi dot right here should be in this equation. So that should be Qi dot uh, here, right? Thank you for pointing that out. Yes, there is a Qi dot. And then d over dt daba L over daba Qi dot. Now I can, let me see. Yes, there should be a Qi dot. And now I can write this whole thing as a total derivative, right? This is equal to the total derivative of Qi dot times daba L over daba Qi dot. So this is a total derivative of this particular expression Qi dot times daba L over daba Q. You can check it, but just by differentiating this one, you should get the answer in the above line. So that is Qi. This is a derivative of two functions that are multiplied each other. So it will be Qi dot times the time derivative of daba L over daba Qi dot, which is the first expression right here. And then you keep daba L over daba Qi dot and take the time derivative of the Qi dot, which will be Qi double dot. Right now it is complete now. So dl over dt will be equal to this particular expression, right? Now you can write this whole thing as a total derivative. You take the right hand side to the left hand side, and what you will get is L minus Qi dot over daba L over daba Qi dot. And this is equal to 0. Right, so this is equal to 0, which means this term right here should be a constant. and that constant is actually the one that we identified as the energy. So the Qy dot times double L over double Qy dot minus L should be equal to V. Now this is a nice result that I will show from an example in the next step, that this constant that we get from this time independence of the Lagrangian is actually the energy. The nice thing here is that even without writing energy, just using this equation, you can find the energy, and you can decide whether that energy is conserved or not, right? And this is what I want you to understand at the end. Instead of just thinking about whether you have a system with constant energy, I mean, the normal way that you would do is just write the kinetic energy, potential energy, and then check whether the energy is conserved. But here is a new way of checking the conservation of energy. So all you need to do is, when you solve it using the Lagrange equations, you write the Lagrangian, and then see whether the Lagrangian depends explicitly on time or not. So if the Lagrangian does not depend explicitly on time, then you can straight away decide that the energy is conserved for this particular system. And at the same time, you can directly use this, what do you call this equation, to find the energy conservation of, to find the energy, right? The value of the energy as well. And once you know the Lagrangian, it's easy, right? You can, that this is what I told you, that the most important part of this particular, this type of problems is understand the system, and then define the, or decide the number of generalized coordinates, and then write the Lagrangian. So once you are done those three steps, everything else should be straightforward. Right? So that's why, uh, that's what I actually tried to convey you, this idea of, I mean, once you write the Lagrangian, then you are like almost like done with everything. Because all the other things you just need to uh, understand, and then keep in your mind. This is a good example for that, for the conservation of energy. So I would like you do this yourself and submit it to the LMS, right? It is, of course, the similar, you have to do the exactly similar thing. I am just not asking anything extra, but once you work out yourself, then you will understand this better. Right, for an example, let me just have a Lagrangian. Uh, that is, the Lagrangian is normally equal to the kinetic energy minus potential energy. And let me have a simple system that kinetic energy depends only on Q's and Q dots, minus, and the potential energy, let's say U, which is a quantity that depends only on the generalized coordinates, which are Q's. Now, uh, I would like this part, keep this part for you. And I want you to go to the calculation and show that uh, for this particular system, Lagrangian does not depend on time. By the way, you can see that there are no time components in the Lagrangian. It's just the kinetic energy minus potential energy, and both these terms do not depend on time. Right now, if this is the case, uh, at the end, show that there is a conserved quantity, which is actually the energy. That energy is equal to T plus U, right? So I want you to do this. and then complete this part in your assignment, right? So this is a very small section, and I will just leave it like that, and we'll write down the note that is if the Lagrangian doesn't depend explicitly on time. So this is does not depend explicitly on time. So that is, the system is invariant for time changes. Then the energy is conserved. Right. This is what you need to uh, understand at the end. And then, so let me go for the next one. That is the homogeneity of this space. And what this homogeneity of space tells you is that when a system moves or translates in space, let's consider a translation like that. Consider a translation. Let me take this. I think we have discussed this last time as well. Let me take a position RA, and let me assume that this particular system that I am talking has translated to a new system which is by an amount of epsilon. This is like you have a system here and then you translated it by a certain amount. Right? So if this is the case, now you can write the variation of the Lagrangian as gamma L over gamma RA and then delta RA. So that's the change in RA. And this will be equal to what? So delta RA means the amount of change, right? That should be epsilon. So that's what. Yes. So this should be equal to 0. And here this epsilon is an arbitrary amount, which means the other term should be 0 for this equation to satisfy, right? So as epsilon is arbitrary, tau L over tau RA should be equal to 0. And when this is 0, now you know that from the Lagrange equations, if I write the Lagrange equation, tau RA dot minus tau L over tau RA equal to 0. So what this means is if this part is equal to 0, and then this will automatically become 0, right, according to the Lagrange equation. And I guess you can understand these two steps, right? The idea is if the system is invariant under translation, right? So what happens? That means the Lagrangian would change even you change the system by a small amount, or if you translate the system by some amount. So that's why this delta L is equal to 0, right? So that delta L means the change in the RA. So that will be equal to this epsilon. And if this variation is equal to 0, the only way that can happen is this particular amount should be equal to 0, right? So that's what I have written here. Then what will happen is, according to the Lagrange equation, when this is equal to 0, the first part d over dt times da by L over da by Ra dot should become 0. And this will give you da by L over da by Ra dot, or the V da by L over da by V should be equal to 0. Maybe I lost the screen, right? So just give me a minute, I will reconnect it. And there are a few issues today here with the screen. Now just understand that the reason that I am taking some time to explain this part about the conservation laws is that in terms of physics, this part is actually very important, right? Conservation laws. Now you can see that all these conservation laws are associated with some kind of symmetry, right? Now, if the system is homogeneous, then that means if you translate the system, it will be the same. Now, the homogeneity means in even in cosmology is that when you look at different directions, the universe looks like the same. Right? So that's the idea of the homogeneity. Right? So which means you can apply the same physics laws, those kind of stuff. But here, what it means is once you try in terms of the Lagrange, the language of the Lagrangian mechanics, the homogeneity means when you translate a system by a certain amount, still you will get the same Lagrangian. So the Lagrangian will not change under small translations if the space or the system is homogeneous. This homogeneity is the symmetry here, and because of that you will see that there is a conserved quantity, and we will prove that this conserved quantity is actually the linear moment, right? Okay, so all right, so this is actually you can write this as a velocity or speed if you like, RA dot, right? So it is the same, and this will be a constant. And if you think about the simple Lagrangian for a free particle, then daba L over daba R dot is what? That is momentum, right? Because you write, let me write that. If you have a Lagrangian for a free particle, that will be half mx dot squared. And if you take daba L over daba R dot, that will be just mx dot, right? That mx dot means the momentum of that particular particle, right? So it will be the same here. So this implies that the associated conjugate momentum, I mean, you can just directly take the, say the momentum here, we used to tell that the conjugate momentum if it is written in generalized coordinates, right? But if it is just Cartesian coordinates, then you can tell like it is just the momentum. So the momentum is conserved. So just keep that in mind. The momentum in Cartesian coordinate is just like mv, but it could be a bit different in terms of generalized coordinates, right? But when you write daba L over daba R dot, that will be the generalized momentum. So now we prove the conservation of momentum and conservation of energy, right? So what other conservation laws maybe we have? So let me write this just to complete as well. In terms of the generalized coordinates, as I mentioned, daba L over, let me say daba Q, A is generalized coordinate. Then if this will be 0, this will imply that the associate conjugate momentum will be equal to 0, not PA dot. Actually, it should be just PA, right? Only the momentum. And this PA is daba L over daba Q A dot. And then this is called conservation of momentum. Actually, this is, even though I tell momentum, that is actually the generalized momentum, right? So this is the generalized momentum. So I hope this is clear for everyone, right? The conservation laws. Actually, what we are doing here is we are actually connecting the these conserved quantities with some of the properties in the space-time. Right? This is actually one of the property that we have in the space-time, that is homogeneity of the space, and this will give you the conservation of momentum. Now, there is a direct way that you can observe this in any Lagrange equation. When you write the Lagrangian, if the Lagrangian does not depend on a certain generalized coordinate, then the generalized momentum uh, conjugate to that particular coordinate will be conserved. Right? You can directly observe it even from the Lagrangian. When you write the Lagrangian, if you don't see a particular coordinate there, and if you see only the velocities, or generalized velocities, that means that particular, or the momentum conjugate to that particular coordinate should be conserved. So let me write it here. So that's a straightforward way of identifying it. When L does not depend on a certain generalized coordinate, so in this particular case, I choose QA as a generalized coordinate. Then generalized momentum conjugate to that coordinate is conserved. Right? This is, and there is a special name for these kind of coordinates, and you may probably have seen this name in your notes. So the QA is also called as a cyclic coordinate. Cyclic coordinate. So that is just a special name that you should keep in mind. Sometimes in the problems, you may be asked to identify cyclic coordinates, right? Because if you have a cyclic coordinate, that is always associated with the relevant conservation of momentum. Now, in general, you also write this as a, let me write it in this way, assume that the Lagrangian doesn't depend on a given coordinate. That is, in another way, if it is, let's say the coordinate is, let's say QJ or something like that, that particular coordinate is cyclic, right? Or you can, if I write the Lagrange equation for this particular coordinate, so let me write QI here, just to keep in line with what I have in the equation. The Lagrange equation is this one right here. Now, yes, let me write this particular coordinate Qj is the cyclic coordinate in the system, because system can have many generalized coordinates, right? So if one of those coordinates, let's say Qj become cyclic, that means for I equal j, so that means that particular generalized coordinate, if that becomes cyclic, so what that means is that particular generalized coordinate, that is Qj, will not depend on the Lagrangians. So that means dava L over dava Qj should be equal to 0, right? So that particular coordinate will not in the Lagrangian, no, it is not a function of the Lagrangian is not a function of that particular coordinate. So that means da bar L over da bar Qj should be equal to 0. And this implies, I mean, it is basically the same thing that I have been mentioning now, right? But this is the general case. So that means this term right here should be equal to 0. D over dt da bar L over da bar Qj should be equal to 0. And this implies that this quantity right here is what we called as the relevant conjugate momentum. So if that conjugate momentum is Pj, that will be equal to 0, and this is conserved. Now the generalized, basically the idea is generalized momentum conjugate to this particular variable, which is Qj, is Pj, and that Pj is conserved, right? So that's how you normally tell it. And in mathematics, we call this as a theorem and a specific theorem. What is that name? If anybody knows who did the mathematics, is there someone who did the Lagrangian mechanics before in mathematics? There is a specific name, I mean, which is we normally don't talk that much about this particular name, but there is a theorem that sometimes these mathematicians know about this. Anybody who did mathematics, we know about this thing. No, actually not that. What we call is as the Noether's theorem. Right? So this particular condition, when you have this conservation of conjugate, when you have a cyclic coordinate, the relevant conjugate momentum is conserved, and that is called as the Noether's theorem. Like in mathematics, and we normally sometimes don't use this, but this name, but we are basically do the same thing, right? I will write this name because I got issues when I was doing classical mechanics courses for my PhD that I did not know this name. I was like thinking for some time what this mean, what actually this means, but it basically the same thing, that because sometimes you get to get the professors who teach classical mechanics, but they have been doing a lot of mathematics. So then they are using this particular name, Noether's theorem. Let me just write it here. In mathematics, this is called Noether's theorem. Right. So that will complete the proof. So we basically talked about conservation of now Sajini, for the isotropic condition, when there is when it is we have this normally when you will learn this in the next semester when you are studying about the cosmology and astronomy, that we normally used to tell that the universe is homogeneous and isotropic, right? And there is a, a meaning for that. When you say the universe is homogeneous and isotropic, right? The homogeneity is what gave rise to this conservation of angular momentum, and what is isotropic? It's actually the same in different directions, right? So if you look at different directions, actually homogeneous is it's same in if you look same in how do you call this? The isotropic is actually the same in if it is measured in different directions, and homogeneous goes in the other way. Okay, so let me. So this takes time. So let me just stop here for the conservation laws, and there is. So we talked about conservation of angular momentum and conservation of uh, conservation of momentum and angular momentum, momentum and energy. And the next component that we know about the conservation laws is that the conservation of angular momentum, right? Um, Now, anybody have any questions up to here? Because I'm going to move into the next section after this. Now, these things about the conservation laws and symmetries that we will, these things will come into play when you are solving problems, right? So these are not the only conserved quantities that we have, right? We have conservation of angular momentum and conservation of uh, other quantities as well. And there are certain times that you have like different interesting quantities that are conserved depending on the system. And we can actually find all these things using Lagrange. Once you write the Lagrangian, you can find those conserved quantities. So we will talk about those when we are solving problems. But other than that, you can ask if any of you have any question. You can ask now, and if not, I will be move on to the next section, which is about Lagrangian, something called Lagrangian multipliers. Now, one example is that this conserved quantity is that if you think about a cylinder that is infinitely long, right? Homogeneous cylinder. So, which means if you consider a particular direction, the cylinder will look like the same, right? Uh, which is a homogeneous direction. And if you consider the c direction uh, of this particular, so let me just write it. This is something extra. So let's say you have an infinitely uh, homogeneous cylinder, and this is, if you consider the z-axis, apart from the other conserved quantities, the angular momentum will be conserved here as well, which we called as LC, right? And these conserved quantities will arise in different problems in different ways, and only thing that you have to look at here is whether this Lagrangian is dependent on a certain coordinate, right? If it is independent of time, then of course the energy is conserved, and if you have a cyclic coordinate, then the relevant generalized momentum will be conserved, right? So that is section of the conservation laws. So if you don't have questions, let me go back to the next section for the next hour of lecture. So the next topic is called Lagrange multipliers. And you can see that everything that we talk now is based on the Lagrange equation, right? Lagrange multipliers. Now, the aim of this particular section is that you have the Lagrange equation now that you can use to solve different systems, but at the same time, uh, these some of these you can only solve a particular set of problems where you have this particular uh, holonomic, which we called as holonomic system, if you remember, right? The constraints that you are talking in all these problems that you have solved up to now, even in the tutorial, they all have these holonomic constraints, right? Which means the constraints can be written from a certain way, and then you are incorporating those into the Lagrange equation to solve the problem. But what happens if you have different types of constraints, and then you cannot use this Lagrange equation to solve that, right? For that, you have to build up a different mechanism to solve those kind of problems. Now, this is what we will do, and there is a certain class of problem that we some used to tell this as semi-holonomic constraints, like certain type of constraints that you can directly solve, you cannot directly solve using Lagrange equation. Now for those, we are going to introduce this new method which we called as Lagrange multipliers, right? So when you know about this, you can solve a different set of solutions, and this is like an extension of the Lagrange equations, right? So let me go through the note now. The constraints can represent as an equation like this, right? So this is the normal constraint equation, and uh, this is actually for a holonomic system. And if you can't remember this, just go back and look at the notes. I mean, even in the first dose, I guess in the second day, we talk about holonomic and non-holonomic constraints and how you can represent constraints from an equation like this. So this is holonomic system. Now, if the constraint equation is like this, then what we can do is we can then the problem can be solved by reducing the number of generalized coordinates. You know that what we did was we uh, have a system, and then we try to identify the constraints. And once you know the number of constraints, it will reduce the number of degrees of freedom, right? Depending on the constraint equations that you have. And then you have these generalized coordinates at the end. And for each of these generalized coordinates, you will get a Lagrange equation written, and then you solve it. So that's how you normally did the problems up to now, even in your tutorial. But there is a different class of uh, problems that you have different types of constraints. Let me take, if you have a constraint equation that actually depends on q's and then q dots, q1 dot, q2 dot, like that. And sometimes some physicists used to call these type of systems as semi-holonomic. I will, yeah, some of them used to call it as semi-holonomic systems. Now, if I can write the constraints in the following form, so let me write, assume that, so let me write an equation. So sum over k, aik, and dqk plus ait and dt equal to 0. If I have a system that I can write the constraints in this form, actually those fall into a different class of problems, and those are the ones that actually we can use using Lagrange multiplier method. So I am going to prove that method and have a different or slightly modified equation for that, so that I can use it to solve this set of problems, right? So aik dqk plus ait times dt, and this goes from I equal 1 to n. So that means in terms of case, you can write one equation, right? By different case, this sum will be expanded and you will have one equation. And this I goes from 1 to m means you can have m equation, right? You can just write. So I is not summed over, k is what is summed over in this equation, but in the same way, depending on your system, you may have maybe 3 equations, 4 equations that you can write it in this way, right? For each equation, you will have a quantity called a Lagrange multiplier at the end, and you will realize it once I am done with this part, right? So let's go through the proof and do an example so that you will have a better understanding what I mean from here. Right, so just let me name this equation because this will be useful in our future calculations. And we have m equations here. M equations that can be written in this form. And the idea is we have m equations that tells us details about these constraints in the system, right? So basically what this means is we have m equations that tells us about constraints. Now, one such example like this, maybe if you remember that we have talked about this on the second or third day when we were discussing about different types of constraints. Let me assume that I have a circle or a disc, a rolling disc, and if this angle is theta, if this is rolling without slipping, uh, you can write the x distance that it travels should be equal to r times theta, right? So I hope you can understand that. What this means is in differential form, you can write the same equation as r is the constant, r is this one right here, r d theta should be equal to dx. And then, you can take r d theta minus dx equal to 0. Right? Now, this is the type of form that we are talking here. You can see that here a I k b q k is in so this particular equation in that type, and you don't have this part right here, right? This is 0. The equation 6.1 is the general equation, but when we apply for problems, some terms may not be there. This is an example for such constraint. Right? Basically, ai case, there are two terms. So there is one term r for one component, a, let's say ai1, and here you have just minus 1 in front of here. So this is basically the type of a11 d theta plus a12 like dx. So depending on the number of coordinates, it goes on like that. But for this particular problem, you have only two components, and the time part is equal to 0. Right? So which means a11 d theta plus a12 dx equal to 0. So this is an example for what for these type of constraint. Right? Now, when you have these differential forms, you can directly use the previous Lagrange equation to solve these type of uh, questions or problems. Right? So that's why we have this new method. And this particular situation, you only have one I, which means one equation. But if the situation is complex, maybe we will have another equation like this. So then it will be I equal to that you will write a21 d theta like that. Right? So that is just an example for you to understand what type of things that we are talking. Uh, so these type of situations, actually these are not holonomic constraints. So this is not holonomic. Holonomic means you should be able to write it in that form that I have given here at the beginning. This one right here. And just to complete the now the problems that involves those type of constraints, problems involves those type of constraints can be solved using a technique called Lagrange multipliers. So this is what we will talk in this particular section, right? About Lagrange multipliers, how to solve these kind of problems. So what we will do here is we will replace the Lagrange equation with a new set of equations, we can incorporate these new type of constraints. Right, so let me, and also we will use the same Hamiltonian principle to prove this. So what we will do is we replace the Lagrange equations with a new set of equations. That involves these new constraints. So it's similar in the previous case. If I take the virtual displacement defined as delta qk, so take the virtual displacement as the delta qk, then I can write this above equation 6.1, which is k times aik delta qk. And there is something that you have to understand here. When we consider a small virtual displacement, remember that we have talked about virtual displacements before, right? When you introduce a virtual displacement, what happened to the second part of the equation? This should be equal to what? 0, right? Because remember the definition in the virtual displacement that that everything is frozen, right? When you define the virtual displacement, frozen means it is defined for a constant time, right? We don't change it over the time. So it is frozen at a particular situation. So just go back to the note about the virtual displacement that we talked just before the D'Alembert's principle or with that. And so we have this definition about the virtual displacement. So because of that, this term should be 0. Actually, you will only see this one, aik delta qk, and this should be equal to 0 according to this equation about the constraint 6.1, right? So let me take this as 6.2, and I am going to multiply this one by a number which I called as lambda I, and I can write it from the outside of the summation. If you can understand that it doesn't depend on k, right? So k is what is summed over to the sigma for one equation, but this lambda I is what we call as a Lagrangian multiplier, and it will be for each constraint equations. So this is what we will call as the Lagrange multiplier at the end. And this one, right, introducing. And you should understand that introducing lambda will do no harm to the equation, right? The equation is aik times delta qk equal to 0. And what I just did was multiply that by a different number, let's say lambda I, right? So it will not change the equation. So introducing new constraint, so the new constant, which we called as Lagrange multiplier. Right? That is lambda I. Now using the Hamiltonian principle and this equation 6.2, I can write using the Hamiltonian principle. And 6.2. So that I can write let me first write this and then after that I will explain d over dt. And then plus so what I just did was I have introduced this a new component called lambda LALK. So that is just, so I just introduced this notation just to keep the indices. But other than that, what I did was I have added this thing called AIK lambda QK lambda AIK, this particular expression from the 6.2 into the Lagrange Hamiltonian principle, right? And then multiplied by the delta QK, which you know as the virtual displacement, right? So when you consider the virtual displacement, then you can neglect that T, so that's what dt, right? So that's what I did here. And this K now goes from, instead of from 1 to n, now it will go from 1 to n plus m, because you have n equations from the general Lagrange equations. Now you have m quantities from lambdas, right? So that's why you change the summation indices. So just to make it clear, let me write it here. So we have n plus m variables or unknowns. So you don't know these things. So which means you probably should have at the end n plus m equations, right, to solve this. And this is done by basically the n comes from nq coordinates, right? So the first n equations, they are actually general Lagrange equations if you have n generalized coordinates. So n, I don't know how to write this, n, this will be nq nq coordinates and m lambda coordinates. So nq coordinates, and then you have m lambda coordinates that come from the Lagrange multiplier equations. Right? Now this will give you the equation that we need, that is d over dt L over qk dot minus L over qk, and this is equal to lambda L ALQ. Right? So like just it was this part, actually this should be equal to 0, right, for stationary values, and this part right here should be equal to 0, and then you make it equal to 0 and get this equation, right? So it's pretty much similar to the proof of Lagrange equation through the Hamiltonian principle, but now I just add this extra part from 6.2, right? Since it was a term that is equal to 0, it doesn't change anything. Actually, just add it, but it will give this new equation that includes Lagrange multipliers, and this lambda L is actually the Lagrange multiplier. And if you have like few constraints, let's say 3 constraint equations, then you will have 3 Lagrange multipliers like that. Now the idea is, instead of solving the general Lagrange equation, now we can solve these 2 equations. So 2 equations means the other one should be the constraint equation, right? I think I didn't write it here, so let me just. Of 6.1, so that is the previous equations. 6.1 is right here, so I'm just writing it here, but you will get it when I'm doing 1 or 2 examples, right? What this actually means. 6.1 is right here. If you take the time derivative, then the dqk will become dqk dot, and then dt will go away for the time derivative. Then you will have aik, and then qk dot plus ait equal to 0, right? So this is what you would get at the end. This will, having these 2 equations actually will help us to, instead of, now previously we had only 1 equation that all the constraints are incorporated inside the Lagrange equation. But here now you have 2 equations. When you have these 2 equations, you can use the 2 equations and probably solve problems when you have these different types of constraints, where the constraint equation have these differential forms, right? And but at the same time, if you have very complicated systems, even in this method, then your equations may get complicated, right? So we will solve some examples and see how it works. So you can basically use these 2 equations to solve it. And before we finish, I just need to go through one example. And this will be example. So once you do few examples, then you will understand this concept behind this one. And this is let me take you. Let's say you have a so I will probably go through a halfway of this example, and I will leave the rest for you so that you will understand and we can discuss it again at the beginning. So let me take this inclined plane, and this angle is phi, and then you have a disk that is again the rolling without slipping, right? So here is the disk that rolls without slipping right here, and this the radius of the disk will be r, and this angle right here is theta. Now, so there is, I have a question for you now. If you have this system right here, there is an inclined plane, and you have this disk that is rolling on the inclined plane without slipping. How many uh, generalized coordinates that you need to explain this system? Is it 1, 2, 3, or 4? So I would like every one of you give an answer for this one. How many generalized coordinates that you would need to explain this system? So there are 4 answers: 1, 2, 3, or 4. So just post your choice here, and you can post it into the chat window. So the question is, you have an inclined plane, and there is this disk rolling without slipping on the inclined plane, right? So all you need to decide how many generalized coordinates that you need. So I will give you a few minutes to think about this, and so I will be back in few minutes. And just think about that, and just post in the chat window the number of generalized coordinates that you think should be necessary or should be needed to explain this system, right? So I have also given 4 answers. It could be 1, it could be 2, it could be 3, or it could be 4, right? Not more than that. So you have to decide what is the correct number. The condition is, once again, you have the inclined plane, and there is a disk that rolls without slipping, right? This is actually a good exercise to select or select to understand the generalized concept about the generalized coordinates here, right? So I will give you some time, just think and post the answer here in the chat window. And also you have to explain why, I mean, we will discuss about that. We will discuss why you choose those answers after that, right? Anyone else have any answers? I just only got one answer from Naveen, I guess. Okay, somebody else told two. And also assume that this is only two-dimensional, which means that the inclined plane is just this line only. So inclined plane, let's assume that inclined plane does not have any tape. Okay, so I guess most of you identified that there are two coordinates, x and theta. Somebody has two, yes, 2x and theta. Let me take, yes. Actually, for the fact that, yes, I got some of the answers, and it is actually two, it is, now you have selected two coordinates, right? Can anyone explain why you selected two coordinates? Most of you tell two. Anybody like volunteer to explain why would you have two coordinates in right? So, I mean, a good way to look at this once again is when you look at uh, the generalized coordinates in the system. Let's say you assume that there is only one coordinate, right? So I assume that the from the x, what you mean is this distance right here from here to here. Let's say you have the distance x up to the point where the disk touches this particular point in the inclined plane. Now you have a coordinate x there. Now the question that you should ask is whether this is enough to fix the disk, right? If it is enough to fix the disk at this particular position, yes, then there will be only one generalized coordinate. So that's how you understand uh, the the number of generalized coordinates in the system. Now, if this is a point particle, then this is correct, right? If this is a point particle, you only need this x. So once you fix the x, that particle will be in this particular position and it cannot move after that. So for a point particle, that will be the only generalized coordinate that you should have. Okay? So there will be one coordinate only. But for the disk, what happened once you fix this distance x? Of course, the disk will be in that particular position. But the problem is disk can rotate, right? So this is capable of rotating on its own axis. And because of that, it will be there, but it is not fixed. It will be rotating. Now to stop the rotation, you have to fix another coordinate. And then you have to identify what is that coordinate. So that coordinate is this angle theta, right? So once you fix the theta, then you are basically done with fixing the fixing this particular object in this particular point, right? So that's what actually, those are the two coordinates that you need to keep the system in this particular position uh, while fixing it here, right? So that's this is why you need two coordinates in this particular situation, and make sure that you, I mean, most of you have told that there are only two coordinates, so that is correct. And what I explain is how you decide the number of coordinates, right? So that is important for you for other problems. So you have only two coordinates, and apart from that, there is actually a constraint equation here. That constraint equation is the condition that okay. So now the question is that if it is rolling without slipping, only need one coordinate. No, actually Naveen, when it is rolling, then actually you need two coordinates, right? Not only one coordinate. Because when it is rolling, I mean, if it is not rolling, then you don't have a problem. No, it will be like here. But I mean, if it is not slipping, right? I mean, if it is slipping, then things get actually more complicated. But when it is rolling, then still you need to have one. Uh, Excuse me, just give me a minute here. So right. So if it is actually rolling, then you that that particular disk has to be at a distance of x, and at the same time it is rolling, right? Rolling is it is rotating. If it is rolling, then you have to fix that particular rotation as well. Now to fix the rotation, then you have to fix theta, right? I mean, if it is slipping, then what will happen is the things get more complicated, right? So it will not be simple thing. So that's why you have this particular condition. Now, I guess the answer may be clear for you now. If it is not clear, then please ask again.
Excuse me,
Right. So
sir.
when you have, sir, yes.
Excuse me, sir. Sir, can we decide that using that equation 3n minus m when finding the degrees of freedom?
3n minus n.
In level 2, we've learned such kind of a equation.
Yes, yes. Actually, this is yes. I know this equation. So what that equation is actually basically give you the same idea. The reason is that normally if you have, so this is how this equation works. Let's say you have a point particle. If it is a point particle, normally you have three coordinates in normal, in any coordinate, Cartesian or spherical or any type of coordinate system. You will have three coordinates. And if you have n number of particles, then you have three n coordinates. For each point particle, you will have three coordinates. For n number of particles, you will have three n coordinates. And then you subtract, let's say you have one constraint. And so this will reduce 1 degree of freedom. Then you subtract 1. Sajini, is this equation tell us 3n minus 1 or?
3n minus m, sir.
Okay, so now I understand. So the m means actually the number of like constraints, right? I mean, if, for example, let's say you have one particle and you have three, which means three coordinates, right? N is like the number of particles. So if you have one particle, there will be three constraints, three coordinates. And then if you have one constraint, let's assume that this constraint is that this particle can move only in a XY plane, not C plane. So which means now you have one constraint, which will reduce one of those coordinates. So that means 3n minus that m should be the number of constraints. If I correct it, if I remember it clearly. So I'm just getting a call from the university. Just give me a minute, right? Right. So I guess the question that Sajini has is I can't exactly remember this equation, but as she is suggesting this 3n minus m equation, as I can see, this should be the number of degrees of freedom and then minus the number of constraints. That is also correct actually, but then you have to find the number of constraints, right, to reduce this. I mean, you should get the same answer from that as well. But what I am explaining here is the idea of all these things is how many coordinates that you need to fix this particular object at a particular position. Right? So that's how you do it. Right? So it is. This is how normally it works. Not sure that how this equation works actually, but I will check this and get back to you in the next time when I start the lectures. Right? So I have noted it down here, whether you have to consider anything specific when you have this particular equation. But as far as I remember, this is number of uh, coordinates minus the number of uh, constraints in this equation that I know. But let me, I will check this and let you know. Right. Right now for this particular uh, setup, let me take this length as L, and then you can write now when the question that Naveen had, when the disk is rolling without slipping, the condition is actually if we have a small distance from here, let's say dx, that dx should be equal to r times d theta, right? And this is in fact is our constraint equation. Now you can take dx into the other side so that you can write d minus dx plus r d theta equal to 0, right? Now here you can see that the two components, let me write ax, the value is 1 minus 1, and for a theta, the value is r. Right? So the Lagrange multiplier equation is something like lambda times r d theta minus dx equals 0. So I'm just running through this because of the time, just to give you some of the information so that like this. Now, now there is another question asking that this equation n is the number of particles, but for a disk, how can we use this equation equal 3n minus m, but actually this n is the number of particles. Now here you have to consider this particle as, let me see, yes, I guess this is a question that I have to think about. So you have n is the number of particles, but for a disk, how can we use this equation for 3n minus m? Okay, so let me check with your notes. I mean, I will check with your notes how this equation came in your second year notes. And I remember that there was an equation like this and how we can incorporate into this. That I will check, right? So I wasn't aware about and I can't remember this equation right now. So I will just, the questions that you have about this equation, I will answer this in the next time by checking it, what exactly is it. And for now, you have this constraint equation, and using this, I would like to go through, like you to go through this example, and at the end, show me that if the acceleration x double dot is equal to 2 over 3 times g sine phi, and the Lagrange multiplier value should be equal to 1 over 3 mg sine phi, and theta double dot equal to 2g sine phi over 3r. So these are the three things, and this is also available in the same YouTube lecture that I have posted yesterday in the LMS about having this the section about the Lagrange multiplier, and this example is already done there. Just go through that example, and I have give you some of the details here, and just prove that these two quantities x double dot, theta double dot, and lambda equal to these values, right? And then post your solution into, I guess this may be a one-page thing that you have to do here. Just post your solution into, I will create a small assignment for the today's lecture, and post your solution in PDF format to there, and I will come back and discuss this again in the next time. And I can see that you have few issues with the things that you have learned before and now about this degrees of freedom, right? I will check that as well. Now for time, since the time is running out, I am going to stop for now. And it is your task for today's lecture is to complete this problem, right? And I have posted relevant materials in the LMS. So you just go to that YouTube video, and it has all these explanations about the Lagrange multipliers, the proof and everything, which will be very similar to what I have done. I mean, I almost wrote the note from that lecture, and you will have this example done there as well. Go through that, try to understand it, and then write it your own words, and make do this proof, okay? And take the values of x double dot, lambda, and theta double dot. And in the next day, I will probably discuss maybe another example using Lagrange multiplier, one or two examples, and then we will finish this section, right? And then you will get another tutorial uh, based on what you have learned up to now, right? And after the Lagrange multipliers, we will move into the next section, which is actually one of the interesting topics about the central field. And this is where we learn about all these motions, how the satellites and how satellite works, and how the motions of the planets are working, all kind of these things, right? Using the Lagrange equation, right? So I'm